You hear this a lot, but I love the subject of gases. It all makes sense. So what I'm going to do is to kind of I'm not going to put the solid and the liquid up, but I am going to go ahead and put my box up here for gases. Okay, and so if we kind of think about gases and think about the general characteristics of gases, no intermolecular bonds, basically, and or actually there's something called an ideal gas, and if it's ideal, there is no bonds, there are no bonds, and have lots of kinetic energy. I'm showing the motion here. So gases are compressible. It means I can squeeze them down. Okay. Gases will actually expand. They'll take on the shape of the container you put them in, and they'll actually expand if you keep expanding this box. So gases will fill the container and the shape and the volume. Density is a ratio of mass to volume. And if you can keep compressing them, okay, you keep increasing the density when you do that. So the densities are infinite possibilities because volume's infinite possibilities. Gas densities are relatively low compared to solids and gases. They're fluffy. They're very fluffy. Okay. Gases. Now, to me, related to the fact that they have so much motion, if you put gases together, they're going to just automatically become friends. One big old mixture. Of course, there's two types of mixtures. There's a homogeneous mixture, which is the same throughout, or heterogeneous mixture. But they're gonna go. One of my husband's things was that years ago they used to have smoking sections in restaurants. Thank goodness they don't do that anymore. But it would be like, so smoke is a gas, particulate. You can smell it, you're interacting with it. So you figure no physical barrier. You have somebody smoking over here, and the fact that actually gases will mix, there's nothing just left on their own, they're going to come over to the smoking section or the non-smoking section. And he likens it to you don't go to the swimming pool, and although little kids usually kind of are in the shallow end, you don't say, well, that's a peeing zone and that's a no peeing zone. So liquids, urine, is a fluid. It just has gases or fluids. So liquids mix like that, and gases mix like that. So anyway, homogeneous mixture, no layering. And gases, we're going to talk a fair bit about pressure. Some of my first slides are all about pressure. Don't get too bogged down in it. But gases come with a punch. And you can almost see the punch if you figure that they are all bouncing against the sides of this container. Punch, 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 punch. Now, pressure will vary depending upon the temperature of the gas. If it's hot, it slows down, less of a punch. And also kind of if it's squished together, okay, more of a punch. Or if it's left below low density, kind of less of a punch, less pressure. So when we get going here, especially on Friday, I'm going to be really honing in on these four variables. So here's my box of gases. Okay, they're banging against that container. One of the awesome things about gases, represented by those dots up there, is that I don't care if it's nitrogen, I don't care if it's oxygen gas, I don't care if it's carbon dioxide gas, I don't care if it's argon gas, I don't care if it's methane gas. It's all going to behave according to these four variables, like who cares what the identity of the gas is. See, that is so cool. So to completely describe the gas, we don't have to say what the gas is. We can if we want to, but we just need to say what kind of punch those particles have, its pressure. We need to say the temperature that it's at. We need to say the volume that's being contained by. And then we also need to say N, the number of moles. So as some of you guys might remember, and I don't want to get ahead of myself, probably get there Friday, but there's something called the ideal gas law equation. You might recognize the P, V, N, and T that are all part of that. The fifth variable is R. In case you're, what is that other thing? Okay, these are all related to each other, independent of what the gas is. All right, so again, I feel like I'm belaboring the point a little bit, but I need to talk about the punch, the pressure. So aside from it, whether it's the pressure of a gas or not, pressure can be defined as force per area, okay? So that's why, like, if I give a punch like this, like I'm not a boxer. Give a punch like this, or give a punch like this, okay, there's less area here, if I have the same force, then that's more pressure. Okay? Where if I have the same force, more area, there's less pressure per area. So I've got some slides to kind of show you that. So pressure, gas pressure. So one of the things that I go, oh yeah, that's how that works, is this idea that in weather they'll talk about the atmospheric pressure, the pressure of the atmosphere. So if you're a weather junkie, you know that if the pressure is rising, you can expect clear skies. When they say that pressure, they mean the pressure of the atmosphere. So what do we mean by the pressure of the atmosphere? Well, one of the things is I'm walking around here, most of the gas particles are running into our nitrogen, about 80% of nitrogen, about 20% are oxygen. So that basically is a punch, 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 punch. So what is that punch? What is that pressure? Well, in general, we're going to talk about different units of measuring pressure. They kind of, I thought this was clever. If you picture your thumb as about an inch by an inch, like a square inch, okay, you hold it out and kind of related to, it's coming from above, but it's also coming from the side, it's also coming from below. You're talking about 14.7 pounds per square inch. Your thumb per square inch. So that's kind of what we have going on. We generally call, so the pressure of the atmosphere. This is kind of talking about that punch versus what sort of area. So the punch here is not like somebody literally swinging their hand. The punch here is actually just allowing gravity to do the work. So if we look at basically the green and the pink is having the same mass, let gravity do the work, then it has a certain amount of force that's exerting downward just to force gravity. Well, the same force, but different areas. So this is to say that actually, if I were to put my thumb here, as an area like that, that'd be a bigger force, be a bigger pressure. Then if I put my thumb here, the force is distributed over a farther, bigger area, so it'd be a less pressure. So these things kind of make sense. Here's one for you, and I just have to take OpenStax at its word. I don't think I'd ever heard this before, but you figure the weight of an elephant is a lot more than the weight of that skater. But if you take the weight of an elephant distributed on its 4 feet, okay, versus the weight of this ice skater distributed on a single blade of her skate. Again, pressure is a function of force, which is the degree of force, over area. This is the less area. This is actually exerting more pressure than elephant. I know. And actually in Chem 2, we'll talk about if you take ice, and I wouldn't have known this unless I had read it or had it described. If you take ice and you squeeze it, if you increase the pressure on solid ice, it's going to melt. I know you're like, oh, yeah, it does. Just trust me, it does. To increase pressure. So the phenomenon that skaters is basically, it's described that right under their blade is liquid water. I know. See? It's not just me, it is cool.
Something I was thinking about too is like a bullet, right? It's got so much force behind it, but it's like,
yes. Yeah.
I guess there's other factors.
Yeah. Yeah. That sounds the same thing.
Anyway, the analysis would say that, like, when a skater lands, I remember saying that there's, like, some constant pressure, a huge amount, and if they land, like, the wrong way, their ankle breaks, like.
It makes sense because it's all focusing. Interesting. So Newton has 3 laws of motion, and his second law of motion is summarized like this: F is equal to ma, where F is force, m is mass, and a is acceleration. And actually, that's kind of the thing we think about when we talk about if something has weight, okay? And it's all about force of gravity, basically creating an acceleration called g. So we're going to come up with g. It's at 9.8 meters per second squared. The force related to the acceleration of gravity on the Earth and its mass. Again, I go too far with regard to pressure. You know, I just basically want you to know the pressure is kind of how that gas particles create against the container that's holding them. But if we take the unit of force, a good unit of force is a Newton, and actually Newtons can be broken down into units of mass would be kilograms, and units of acceleration would be meters per second squared. So force, that punch, that that Newton is kilogram meters per second squared. We'll be talking about different, so I bet this works for you. We said that pressure is equal to force divided by area. Okay, and I said force is newtons and area meters squared. I buy that. Pascal actually is a unit of force, and it's not one we're going to stick with, but it's a nice basic unit. I bet they use it more in physics than we do in chemistry. This topic actually of gases overlaps between physics and chemistry. So if we're not going to work with pascals much, which unit of pressure are we going to interact with? And you know how I used to do the whole arrow means you have to memorize? Okay, that's what it means here too. So I mentioned a little bit ago that it's not just your thumb, but your thumb is about 1 square inch. But right now we're running about 14.7 pounds per square inch of punch on the gas particles. In terms of units of atmospheres, that's approximately equal to 1 atmosphere. So pounds per square inch, or PSI, has approximate relationship to atmospheres. So in working gas law problems, we do a lot with atmospheres and millimeters of, what element does Hg stand for? Mercury, yeah. So 760, we usually say 760 millimeters of Hg, and I'm going to have to try to describe millimeters. You're like, millimeters? Really? Yeah, millimeters of Hg. So I'll kind of show you how we get to units of pressure like that. Here we have, this one. This one you should probably memorize too, but it's not too bad. We don't see the unit of pressure of torr very much, but it seems like I think the lab you're doing a week from tomorrow, we use units of torrs. In terms of the torr is exactly equal to, torrs and millimeters of mercury are exactly equal, 1 to 1. And then here is your pascals and bars. And actually, when it comes to meteorology and weather and all that, a lot of times they will talk about MBs. MB stands for millibuffers. So, cool. So this actually is a liquid mercury barometer. Now you're like, mercury, I know it's a liquid under normal temperatures and pressures of the Earth, and you're right. It's that kind of the silvery color to it. So how do barometers work? And they don't all have to be mercury. So I kind of have a silly water barometer to show you here in a minute. Mercury's good because it's nice and dense. What you do is you take a piece of glass tubing and you go ahead and suck it clean of air. That kind of thing. You evacuate it, and then you put your thumb over the open end and you put the open end into the pan of, in this case, mercury. And then what happens is, it's going to seem strange, but your liquid actually will climb up. Now, how far will it climb up is relative to the pressure this is weird to me, the pressure that's being exerted on the pan of liquid that your open bottom is connected to. So in other words, if I increase this pressure, why would it increase? Well, it's actually a function of the nitrogen and oxygen in this room. I increase this pressure, the mercury's going to go higher. If I decrease this pressure, the mercury's going to come down. So then a little bit ago, I said that 1 atmosphere is exactly equal to 760 millimeters of mercury. That's where your 760 millimeters comes. Basically the base of your liquid up to how far your liquid climbs. So that's a liquid mercury barometer. Notice a few things. It doesn't depend upon the diameter of the tube, which is kind of cool. All right, so this was the silly one I was telling you about. So for instance, we've got 2 barometers here. One is using mercury as the fluid, and one is using water as the fluid. Of course, in both cases, the way we created the barometer was to take a tubing that's closed at one end, suck out the air, go ahead and invert it in the liquid. So this one would rise, for instance, we're a little bit above 1 atmosphere. We're running a distance. The distance to be measured would be from the liquid up the glass. You're running 790 millimeters, which is more than 760. Well, because the density of water is so much less than the density of mercury, at the same pressure, you would have to go, instead of 2.5 feet, you have to go 33.9 feet. So water's not a practical thing. It can be used, but it's just not practical. I think that's funny. Have some things to kind of show you from left to right. The first one's kind of silly, this first one over here on the left, because look, it's open at the end. What does that mean? Well, it just means that the liquid mercury is going to kind of settle to wherever you have the tube, okay? Then we get to kind of not silly over here. The difference between B and C is just the height of the tubing. So B and C are like usual barometers where we closed one end, okay, sucked it out, inverted it, moved my thumb and let it kind of settle. Notice that even though I give it more length, it's only going to go to a certain length. That's the height that's indicating what we would call the atmospheric pressure, millimeters of mercury. By the way, again, back to weather. Weather, oftentimes I mention millibars, but even before that, usually weather, that the pressure of the atmosphere is given in usually inches. You're like, ugh. So there's actually some labs that we do with gases where I have to convert inches of mercury, which is what the weather people says, to millimeters. So I think that's interesting. So what's wrong with this one over here? What's wrong with D?
I don't know.
Yeah, they kind of shortchanged it. And so this one would not tell you the barometric pressure, okay? Because it was stunted, it wasn't allowed to go up and down.
So, sorry, I kind of missed the liquid at the bottom is mercury.
Yep, the liquid at the bottom is mercury, yep, and it's allowed to, it will climb up this tube that's closed at one end that had a vacuum in it before. It will climb up relative to what this pressure is on the pan of open mercury. So.
Okay, I don't remember the reason for this, but why do we as like the imperial system everybody else uses the metric system?
Why do we have the Old English and everybody else uses metric? I don't know. I think it's, I don't know if, I don't think it's, it might be political. And it could be that the changeover is going to cost some money, you know. You figure to redo things, you know, like just take our gas pumps. Instead of gallons, of course, those would have to be liters. And that's going to cost money to redo it. I think they want to pay.
Like, how did you even come about that? You know what I mean?
Well,
Like, everybody else is using that. Or I guess,
I think,
is metric a newer thing?
yes. I believe metric is newer.
So we just have an update.
We just have an update. Yes. Yeah. That would be kind of how I would think of it. Because they call it the English system versus the metric. So the English would be, that's kind of what we brought over. Yeah.
Okay.
It's still not good. Like, I guess, and I haven't been, but if you go to Canada, I guess the speed limit signs are in kilometers per hour instead of miles per hour. So, if you buy cars, and you can go back and forth between those two types. Yeah, we should Google that. You get it started, Danielle, and I'll sign your petition.
I mean, it would be huge.
What's that?
It would be a huge thing.
It would be a huge thing, but come on, people. Yeah. This one, actually, I'll tell on myself. I had to open up. I don't think I've opened up the OpenStax book this semester, but I had to follow up on this. So first off, this is called a manometer, which I don't know why they call it a manometer. It's just to measure pressure. Now, when dealing with gases, you usually have to kind of identify your gas of interest. So the way a manometer works is our gas of interest is right here. You guys remember your burettes, okay? And you had stopcocks on your burette? Okay, that stopcock is parallel to the gas tubing, which means it's totally open. Okay, so that's open. And then what we have here, I don't know if you guys can see it very good, but this is the gray. Okay, so this is mercury. Now, why do we choose mercury? Well, it's nice and dense. And we're assuming that it's actually not reactive with the gas of interest there. So think of it this way, when the gas fills the tube, the bulb up there, it's going to go ahead and travel down and eventually start banging on that mercury. So depending upon the pressure of the gas, it will bang on it, so it makes it go down, it makes this move down, and this moves up. Now, if the pressure in there decreases, guess what? Then that means that mercury won't get displaced as much. Okay, so that's a manometer. So the way this works then is the pressure of the gas is equal to, now does that look like a P to you? That looks like a P, HPG. Well, it's not, it's rho. It's the density, okay? H is the height, right here, and it is above, in this case, where it's open at the top, above where this is. P is rho, that's the density of mercury. And G would be that thing I mentioned before, the acceleration due to gravity, the thing that we use to calculate the weight of things. That's at 9.8 meters per second squared. So anyway, the pressure of the gas. But bottom line, like I said before, as the pressure of that gas increases, what happens to the height? As this increases, what happens to this height? Does it go up or down? It goes up, yeah. So pressure increases, height increases. Now these are a little bit different. Oh, sorry, that was closed at the top. That's closed at the top. These last two are open. And the way this works is, again, you can see that we have the gas of interest in our little round bottom flask up there. And it's open, and we can see it's beating on this mercury, but can you see where actually, oh yeah, check this out. What do you think? To me, what that says is this is kind of like a straw, sucking it. So actually the pressure of your gas is less than the pressure of your atmosphere at that point. Make sense? And you can go ahead and actually kind of do a calculation where the pressure of your gas, the pressure of the atmosphere minus that height. This other one then kind of changes it up a little bit, and like the second one, it's open to the atmosphere, but now we're blowing, and like blowing through a straw. So actually this would mean that the pressure of our gas was greater than the pressure of the atmosphere. So anyway, those are manometers. So now I'm going to go ahead and walk you through. This is good. I think we'll get through. I said P, V, and T. That's kind of the order I think of it. And so beginning Friday, we're going to be kind of looking at those, how those kind of play together, again, independent of what the gas is. But we're going to kind of take them pairs. So now we're going to take pressure and temperature, and we're going to assume that volume stays the same and N is never mole stays the same. Okay? And we're going to use a mathematical symbol called a proportionality symbol. So here is your proportionality symbol. Looks like an infinity sign with a bite taken out of it. So the way you would read that little mathematical statement is we would say that pressure is proportional to temperature. And I'm going to go ahead and throw in the word directly proportional. So pressure is directly proportional to temperature. That means that if one goes up, the other goes up. One goes down, the other goes down. That's mathematically what directly proportional means. Okay? And it makes sense. Like, there's so many examples. Like, if you buy a balloon, I don't care whether it's the latex or the mylar? Yeah, latex or mylar balloon. And you buy it on a cold day like this. And it's cloudy out, and so your car doesn't get hot, your car gets cold. So you go and you buy it at Hy-Vee, and you put it in your car, and then at Hy-Vee, those gas particles are bouncing and extending that, making it nice and tight, okay? But then when you put it in your car, the temperature goes down, so the pressure goes down. So when you go to grab your balloon, like, dude, they shortchanged me on helium because it doesn't. It's not. I don't feel the same pressure. Temperature went down, pressure went down, and it kind of makes sense because I don't know if you've ever bought ants in the mail before, but ants in the mail, if they come in the wintertime, they're all lethargic. Okay, and that's a function of temperature. So basically, they slow down and they don't create pressure.
So I've noticed that kind of like with water bottles, I guess. Like I buy an empty water bottle in my car and it's cold outside. It'll like start like keeping on itself a little bit, and then bring it warm.
Same thing. That's totally it. That's totally it.
So it's the pressure inside the container that decreases.
So in the case, to me,
And
that
then
I know.
outside pressure
Right. Yeah.
it stays the same, but it's greater than the pressure inside.
Right. Yep. It's nice and sealed, the water bottles you buy. And to me, it's because you figure there's liquid here, there's just a little bit of headspace of air. And to me, it's that air that's doing it. That air that's changing the pressure, not the liquid itself, but just in that headspace above the liquid.
But I was talking about like even like a completely empty water bottle too.
Okay.
Like it'll like
Oh yeah. It has a lot of air in it. Yeah. That makes even more sense. It's all no liquid, then it's all this gas that's responding to air. Yep.
Okay, so like when a bottle and a bottle.
It could be. It could have been made that with temperature changes.
you ever done the little thing where it's like really cold water and you like touch it and it like releases the whole thing? I accidentally did that one time. I think it was last winter. And my mom had some water bottles in her car and they're all liquid and like I picked one up and went I was like, whoa.
It's liquid that's cooled below the freezing point temperature, called super cold. So it was like liquid water at 30 degrees Fahrenheit. It should not be liquid. And so it's a very tentative thing, and you open it up and it.
Wait, so why does it stay liquid? How does that start?
It has to do with how it's cooled down, just so slowly and carefully I say without being disturbed, but sometimes I've had it before in like the back of my car, so it's not like they're kind of like bugs. So, but it has to do with how it's cooled down. It's kind of hard to recreate sometimes if you're trying. But it is very cool. Oh, movie time! Bottle pop in your freezer, then it expands. Create a mess. So here we have a round bottom flask, and we have a cork in the top. The top in the cork is actually inserted pressure meter. So we do a lot of these kind of figures. So the way that pressure meter works is the more it is over to the left, the lower the pressure is. So again, we're talking about volume versus pressure. So here we have a hot plate on medium. So what happened to the pressure valve? It went up. Yeah, it went to the right, exactly. And here we go. We jack up the temperature, and at high temperature, what about pressure? High pressure, yeah. So, I mean, gases are gases. You don't see them, but we can understand things about them. It makes sense, and actually here we're actually seeing it do it. So I'm going to show you the relationship between pressure and temperature, But the problem with gases and temperature is that the temperature scale that works the best is the Kelvin temperature scale. Remember we talked about Celsius and Kelvin, and they're both metric. They both kind of want Celsius and Kelvin. But the cool thing about the Kelvin is that that's why it's like the ratio level of the measurement. The cool thing about Kelvin, no pun intended, is if you go 0 Kelvin, what's the significance of 0 Kelvin? Can't get any colder, exactly. And how fast are particles moving at 0 Kelvin? They're completely still. So as long as we come up with this kind of cool plot between pressure and temperature, and it looks like this. So this is actually, in lab I talked about extrapolation a little bit. Interpolation means you're looking at your data points and you're like, oh dude, I can kind of, like you did a lab where you took off, weight percent, picked off density, and then from that you picked off weight percent. Okay. So interpolate would be, here's some data points here. Extrapolate is what we're doing here. Okay. So extrapolate says, all right, so if I continue to, my last data point's at 200 Kelvin. If I continue to get colder, my pressure should continue to decrease. And so here we go. We are extrapolating back to what's 0 Kelvin? Absolute 0. Yeah, absolute thermal energy. Yep. So at 0 Kelvin, we should have a 0 pressure. So cool.
That Celsius just reminded me that the other day I think it was this weekend, I was talking to my 6 weeks ago, and I was asking her about the weather that day, and she said that it typically stays between. She said the coldest it would get there is 15 degrees. And I was like, oh, that's so cool. But I realized she was talking about Celsius.
See, they're with it. Celsius is the metric.
Yeah.
Wait, yeah, and Fahrenheit is the.
So then I was like, and she's like, the warmest is 30 degrees. I was like, what do you mean? That's so cold. And then I was like, oh, yes.
No doubt. No doubt. I'll double check, but I'm thinking that these are wrong. Do you guys remember how you convert from Celsius to Kelvin? So let's see, which way do you want to do it? Say you want Kelvin. You take the degrees Celsius. Do you add or subtract 273? Wait, no, I see that. Sorry, degrees Celsius equals Kelvin. Well, my point here is 0 Celsius is actually 273.15 Kelvin. So I don't know where they got that from. So I wonder if they just, this one goes here. I bet they just offset it. Do you know what I mean? Yeah. So sorry, if you want to do those arrows on your slide, you can. Because 0 Celsius is 273.5, 273 Kelvin. Okay, so 100 Celsius is 373 Kelvin. Negative 100 Celsius is negative 100 degrees Celsius is negative 173 Kelvin. So, sorry. So anyway, I think that's a good place to stop, you guys. Good questions and all that. And congratulations, we did not get through this first part. And I should be in my office tomorrow, what did I say, 9:30-ish?